In this section, we will introduce event-driven programming and how to implement it using the event structure. Imagine that you need to create an application in which an event on the panel, like changing the value of a particular control, will trigger corresponding code on the diagram to execute. For example, notice that each time I change the temperature, degrees Celsius control, the application returns the temperature in degrees Fahrenheit in this indicator. And each time I click the Check Time button, this triggers the application to return the current time and date in this indicator. And each time I click the Acquire Data button, this triggers the application to acquire data and return the data in this graph indicator. And when I click the Stop button, the application stops. How would you implement this functionality on the diagram? One way to implement the previous functionality is by constantly polling the values of the controls on the panel in a loop to check if any control values have changed. Here, you can see that this code uses a shift register and a not equal node to determine if this temperature control has changed its value. If it has, then the case structure will execute the true case. Here, you can see that this code continuously checks if the Check Time button is true, and if so, will execute the code in this true case. Similarly, this code continuously checks if the Acquire Data button is true, and if so, will execute the code in this true case. The false case of all these case structures is empty. However, there are problems with polling. Constantly polling the control values requires CPU usage, and polling can fail to detect changes if the value changes too quickly. In this example, if you click the Acquire Data button 2 times very quickly within one polling loop period, so that the value goes from false to true and back to false very quickly, the diagram might never read the true value because you changed the button value back to false before the diagram had a chance to read that value. The best way to implement event-driven functionality is to use an event structure instead. Benefits of using event structures include the following. It reduces the CPU requirements of the program, simplifies the diagram code, guarantees that the diagram can respond to all interactions the user makes, handles all events in the order they occur, and does not miss any events. Event-driven programming is a method of programming where the program waits on an event to occur before executing the code written to handle that event. An event is an asynchronous notification that something has occurred. Events can originate from the user interface, external I/O, or other parts of the program. Right now, you will only learn about user interface events, such as value changes of a control. With user interface events, you can design an application so that LabVIEW generates an event each time a user performs a particular action on the panel. Each time that event occurs on the panel, the diagram responds by executing the code you wrote for that event. Let's run this example VI. When I change the value of the temperature control on the panel, an event occurs that triggers code on the diagram to convert the temperature to degrees Fahrenheit and display it in this indicator. Similarly, there are other user interface events defined in this VI that trigger other code on the diagram to execute, such as changing the value of the Check Time button, changing the value of the Acquire button, and changing the value of the Stop button. Now let's show the diagram and turn on Highlight Execution. As you can see, user interface events on the panel, such as the ones demonstrated here, can trigger the execution of diagram code that you wrote to handle each event. You should use an event structure to implement event-driven programming. You configure which events you want the event structure to handle. The event structure can have multiple event cases, each of which is a separate event handling routine. When the event structure executes, it waits until one of the configured events occurs, then executes the corresponding case for that event. The event structure completes execution after handling exactly one event. The event selector label indicates which events cause the currently displayed case to execute. You can click it to view the other event cases configured in the event structure. The event data node identifies the data that LabVIEW provides when an event occurs. The node provides different data elements in each event case of the event structure, depending on which event you configured that case to handle. For example, the event data node for a value changed event includes old value and new value items. You can also resize the event data node, and as you can see, you can access the data. When using event structures, you should usually place the event structure inside a while loop. The event structure handles exactly one event per iteration of the while loop. To configure an event structure event case, first, select the event structure case you want to configure. Second, set the source for the event, for example, a particular control on your panel. Third, set the event, for example, a value change for that control. Now let me demonstrate how to configure and use events for our example application. Here, I have a VI that contains a temperature degrees Celsius numeric control, check time button, acquire button, and stop button. First, I will place down a while loop. Then, I will place down an event structure. Then, I will configure this event case to respond to a value changed event from the temperature degrees Celsius numeric control. Now I will create the code that will execute when this event occurs. I want my event structure to respond to some other events too, so I'll click Add Event Case here. I will configure this event case to respond to a value changed event from the Check Time button, and create the code that will execute when this event occurs. Generally, if you're creating an event for a value changed event on a Boolean button with a latching mechanical action, it is best practice to place the Boolean button inside that event case. That way LabVIEW will read the Boolean button, which causes the button to go back to its default value. Now I'll add another event case to handle a value changed event from the Acquire button. Lastly, I will create another event case for a value changed event from my Stop button. Now, I'll run this VI and test my event handling code. You can also configure a timeout event case that will execute if a specified number of seconds elapses and no events occur. To do this, add a new event case and set the event source to application and the event to timeout. Notice that a timeout input now appears. The timeout input specifies the number of milliseconds the event structure will wait for an event before the event structure will time out. The default value is -1. Which specifies to wait indefinitely for an event to occur. If the event structure times out, it will execute the code in this timeout event case. Now, if this event structure waits 1000 milliseconds and no configured events occur, this event structure will execute the code in the timeout case. In this section, we will discuss how to create an event-driven application with the user interface event handler design pattern.
Okay.
The user interface event handler design pattern consists of an event structure inside a while loop. Each event case of the event structure is configured to handle a UI event, such as a value change of a control on the panel. Each event case also contains the code to execute each time that event occurs. The user interface event handler design pattern is good for applications where user interface events, like value changes, need to trigger the corresponding event handling code to execute. The event structure handles events in the order they occurred. For this design pattern, the event handling code should be short and quick. Now, I will walk you through the application you will create in the following exercise using the user interface event handler design pattern. First, I'll run the VI to demonstrate its functionality. As you can see, each of these value change events triggers some diagram code to execute. Let's take a look at the diagram. Notice that there is a while loop and an event structure. Additionally, there is also a shift register. This shift register holds the current value of the acquired data. Storing the acquired data in the shift register allows multiple event cases to update and read the current acquisition data. When the user clicks the Generate Stimulus button, this code generates either a 0 volt or 5 volt output, depending on whether the button value is on or off. When the user clicks the Acquire button, this code acquires data and stores the acquisition data in the shift register. When the user clicks the Analyze button, this code reads the acquisition data from the shift register and uses a sub-VI to process the data. When the user clicks the Save button, this code reads the acquisition data from the shift register and logs it to a user specifier. These are some caveats and recommendations to remember when using event structures. This state diagram shows the logic of the user interface event handler design pattern. This design pattern waits for an event, and when an event occurs, it will execute the corresponding code to handle the event, and then go straight back into waiting for an event again. What if you wanted more complicated state diagram logic to handle an event? In this section, we will discuss a powerful and flexible design pattern called the Event-Driven State Machine design pattern. The Event-Driven State Machine design pattern combines the user interface event handler design pattern with the flexible transitions of the state machine design pattern. This design pattern allows you to have an event-driven application that can respond to events by executing more flexible state diagram logic. To do this design pattern uses a state machine that includes a wait for event state. The purpose of the wait for event state is to wait for an event to occur and then transition to the corresponding state that will handle the event. So the wait for event state contains an event structure, which waits for its configured events. When one of those events occurs, the event structure passes the corresponding next state to the state shift register. Let's take a look at an example of an event-driven state machine that implements this state diagram. As you can see here, the first state this state machine executes is the initialized state. Then the initialized state transitions to the wait for event state. The wait for event state then uses the event structure to wait for an event. Let's say the user clicks the Acquire button. The event structure will execute the Acquire Value Changed event case, which tells the state machine to transition to the Acquire state next. The Acquire state acquires data, and then transitions to the Analyze state next. The Analyze state analyzes the data, and if the data exceeds the threshold, the state machine will transition to the Log state next. Otherwise, the state machine will transition to the Update UI state. The Log state logs the data to file, and then transitions to the Update UI state. The Update UI state passes the acquisition data into the graph indicator, and then transitions back to the wait for event state. You will create this VI in the next exercise. LabVIEW NXG includes a template for the event-driven state machine design pattern. Open this template by going to the Projects tab, New tab, and then click Simple State Machine. Now, let's take a look at a caveat and potential problem with the event-driven state machine. What would happen if a UI event triggers code that has a duration of 30 seconds? Will the UI remain responsive while that 30-second event handling code executes? Let's observe what happens if one of the states in an event-driven state machine contains code that takes a long time to execute. I will modify this acquire state by adding a wait node. So now the acquire state takes 15 seconds to finish executing. Now I'll run the VI and click the acquire button. The diagram code is now stuck in the acquire state for 15 seconds. In the meantime, notice that my panel looks unresponsive. The latching boolean button will stay pressed instead of latching back to unpressed, until the state machine is able to go back to the wait for event state so the event structure can read the button. After the 15-second acquire state is finished, the application becomes responsive again. This shows how having a state with a long duration can make the event-driven state machine seem unresponsive. In this section, we will discuss the concept of the producer-consumer events design pattern. Message communication describes when you intermittently transfer messages between loops, and each message might also include message data that can use whatever is the most appropriate data type. For example, every time a user clicks a process data button, the application can send a message that includes the data to process to a separate processing loop. In this message communication example, loop 1 is sending both a message and message data to loop 2. When the application starts running, loop 1 sends an initialized string message with a numeric 0 as a corresponding message data. Later on, loop 1 sends a process message with the message data 100 to process. Then the application wants to log some data, so loop 1 sends a log message along with the log data 50 to write to file. These messages can get queued up if the receiving loop is busy, so the receiving loop can process the messages in the order received. Also, we can send a high priority message, such as emergency stop, to get read next ahead of normal priority messages. So in this example, we have seen some common characteristics of message communication. One way to implement message communication is to use the producer-consumer events design pattern. First, we will send our messages and message data from a producer loop to a consumer loop by using a queue. We can make our queue element data type a G-type cluster that contains a string for the message, and in this example, an integer for the message data. The purpose of the producer loop is to enqueue a message and its message data when an event occurs, and to keep the user interface responsive. The producer loop waits for an event to occur using an event structure. Each event case just sends the message and message data that corresponds to the event to the consumer loop. Because the code in the event cases do not do any intensive processing, the event structure in the producer loop is always ready to respond to the next event.